to 1. But what I have is a bunch of data, and the data look like this. So here's x. And when I look at my data, so I have, one data point here, 2 here, 3 here. Something that looks like this. Okay? So maybe it's even worse than this. Maybe I have a couple of data points out here. So clearly it doesn't look like a Gaussian. This is my x given y. So I want to represent this with a density function. Why do I need the density function? Because I need to be able to describe the likelihood. So how do I do that? Well, the way to do it is to plop a kernel, and I'm going to show you what a kernel is, at each data point. And when you have a data point, you would just plop a kernel on top of it, and the more data points you have, the more kernels you build up on top of each other. Then what happens is that you need to normalize the whole set so that the integral of your distribution is 1. So that's what kernel density estimates do. So our kernel here, kernel as a function of u, so I need to separate what u is from x. So suppose that u is my variable, and kernel is k. And we're going to describe what this kernel is. Kernel is going to be just a Gaussian sitting at a particular data point u. So this kernel is just something that I'm going to have at the data point u. So when I say form a probability p of x, suppose that I take all my data points that belong to class 1, and I'm going to now formulate my density function as follows. I have n data points that belong to class 1, and I'm going to sum up all the k's where each point for where I plopped my kernel was on top of my data point. So this is going to be x minus xi divided by h. So this is function of u. This is how I define u. K of u, its function is described like this. And for u, for each data point that I have, I'm going to give it this function. What is h? What h does is the smoothing of this kernel. So this kernel is going to be really sharp if h is small. It's going to be broad if h is wide, right? So if h is large, it's like a variance. So if h is large, what you're doing is you're plopping a kernel that has a lot of breadth. If h is small, you're saying, I'm going to have a kernel that's really sharp. What that means is that when you end up computing your density, you're going to get, things that look like this. If h is 1, you're going to get something that looks like this. If h is 2. And everything in between. Depending on how sharp do you want your density function.
Does it also depend on, that's just a design parameter.
Yeah.
So like if your x is quantized,
yes.
or you could pick a narrower.
Right. Right.